Test, test. All right, what's up? Um, so I'm hoping people have questions over pretty much everything, and I'll stay on here as long as I can. Oh God, and I'll answer questions as long as I can. Ideally, you have gone through the questions I put in on campus, both for the chapter one test, for the chapter two test, for any quizzes, and the that handout I gave out for from the AP Calc book. I'll bring it up here in a second. But if you have questions, tell me what it's from, tell me the number, tell me the page, and I'll do it as best I can to explain it and to show you how I would do it and the best way to do it and whatever you need. Obviously, a major part of this test is going to be just from what you see up on the screen. I'm going to put a couple more things up there that's going to help as well. But yeah, this is going to be most of it. Will squeeze theorem be on the test? Not totally. Some of the stuff you do with the squeeze theorem is going to be on there, but it's going to be stuff that doesn't explicitly have to do with the squeeze theorem. Okay, it's gonna it no. In short, no. So this is for you. I'm like not prepared for this at all. This is all about you guys. So any questions that you have, say it and I'll go through it as best I can. So I'm gonna mute myself for a second. I'm gonna put a couple more things up on the screen, and then I'll start doing questions that people have. Okay. Limit as x approaches 0 of sine of x over 5x. Great. Okay. So, really simply, we can factor out a 1/5. So this is going to be equal to the limit as x approaches 0 of 1 divided by 5 times sine of x over x. The limit rules tell us we can take this 1/5 and put it out front. So this is going to be 1/5 times the limit as x approaches 0 of sine of x over x. This is a limit that we should know. The limit, so this part right here, that's just equal to 1. So it's 1/5 times 1, which is just 1/5. No, you're not going to need to know arc cotangent. Anything I haven't, well, yeah, probably not. Things you probably won't have to know on this. 20 and 22, you probably won't need to know. You definitely won't need to know. I'm not going to ask you about them. Number 8, I'm not going to ask you about. And number 11, I'm not going to ask you about. Everything else is, I think, is fair game. Maybe number 12, I'm not going to ask you about either. Everything else is completely fair. Those are the ones we focus on the most, so I think we should all know this pretty well. If people don't have questions, I'm going to just start doing random problems. I just got to pull up my pages. So I'll do number 11 on 1 or 206. So this gives you a graph, and it asks you to find an equation of the tangent line to the graph at the given point. It gives you graphs of them. It doesn't really matter. This graph is given by x to the 2/3 plus y to the 2/3 is 5. And we need to find the equation of the graph at 8, 1. Okay, so this is similar to what was on the chapter 2 test. It had the one that on the chapter 2 test had like e involved and all that stuff, but this is just as valuable. I'll go over those next questions. Just let me do this one first. So we differentiate it all. Okay, so we take the derivative of both sides. The derivative of x to the 2/3 is going to be 2/3 x to the negative 1/3. The derivative of y to the 2/3 is 2/3 y to the negative 2/3 times dy dx. The derivative of 5 is 0. and that's our derivative. Okay, we need to find the equation of the line at 8, 1, so we need to find the slope of the line tangent to that graph at 8, 1. So we plug in 8, we plug in 1. Eight to the 1/3. That's 1 over 8 to the 1/3, which is 2. So that's 2 over 6 plus 2/3 dy dx is 0. And then we solve for dy dx. So 2/3 dy dx. I'll answer a bunch of these questions here in a second. I started this problem before people started asking. Okay, so that's our slope. And then we have a slope and a point. And that's your equation of the line. All right, so finding tangent lines, equations of tangent lines to graphs, that's going to be really important. You're going to have to do that. Okay, so a couple questions. Squeeze theorem, again, not explicitly. We did the limit of x approaches 0 of sine of x over 5x. We don't need to know arc to cotangent. No, we don't. Page 207, 131. Let me answer these other ones first because that's going to be a little bit easier. Limit as x approaches 0. I'll get to that. Infinite limits as a whole, like number 13 on chapter 1 test. Okay. So there's a Q. When in our notes did we go over sine, cosine, tan as limits? This is chapter 1. The special limits, I think, was like 1.3. The limit of sine, cosine, and tangent was like earlier. I think it was like 1.2. But if you're taking the limit of like sine, all you're doing is you're plugging in that value. Same thing with cosine and same thing with tangent, unless you get a 0 in the denominator. That's like the only thing that you have to worry about. Find an example that you're struggling with, and I'll try and do it. Will Newton's method be on the test? Yes, there will be one Newton's method. Okay, so let's do 207, 131. Okay. All right, great. So we have an airplane flying in still air with an airspeed of 275 miles per hour. The plane is climbing at an angle of 18 degrees. Find the rate at which it's gaining altitude. All right, so we have a triangle. With an 18-degree acute angle. That's going to be a right angle. And this depends on how... If this were me grading it, I would grade this in two different ways because it's not totally clear. I forgot how we did this on the board to get the right answer. I think we're going 275 horizontally. So we'll name this side A. So we'll call that dA dt. We'll call this side B. We need to find dB dt. And this side is C. It doesn't really matter. You don't need to find dC dt. So we need to find dBdt given all of this stuff. So what we would do is we need an equation with a, b, dAdt, dBdt, and 18 degrees. So if we're looking at this, we have an opposite side and an adjacent side. Tangent's going to get that done for us. So we have tangent of theta is going to be equal to b over a. We could solve for theta just to make it easier on us later. So if we take the arctangent on both sides, we're going to be left with theta is equal to arctan of b over a. And then we need to take the derivative of that. So d theta dt is going to be 1 over oh, you know what? I know a better way to do this that I'll show you here in a second. If this were a real rate of change problem, I would do it this way, though. I forgot. This is actually a lot easier than it needs to be. But we would set this up. Right, the derivative of arctangent is 1 over 1 plus the thing on the inside squared, and then times the derivative of the thing on the inside, so that would be a dB dt minus b dA dt over a squared. We would plug all this stuff in. The great thing is d theta dt is going to be 0. Right, this 18 degrees isn't changing, it's constant, so there's no rate of change, so it's 0. We would get, yeah, okay, this is where we ran into problems, that's right. So you don't really have to do what I just said, but I'm going to run through the logic for it. We would plug in b and a and dB dt and solve for, and dA dt, and then solve for dP dt. The great thing is you don't really need that. This is just a right triangle problem. So if you want to skip all that hard stuff, literally you just need to do the tangent of 18 degrees is equal to dB dt over dA dt. I think that's how we did it. That's going to be 275 times the tangent of 18. I think that's right. So if we plug that into a calculator, what'd I do wrong here? That's not right. So I know Winkleman and O'Leary and I did this, and we got the right answer. I just forgot how to do it. Um, my initial guess was this stuff, but we don't have an A and we don't have a B, so those don't matter. We need a DADT, a DBDT, and something with 18 degrees. So, okay, I'm going to draw this again. And this is where this question is a little bit annoying. It might mean this is going 270 miles per hour. And we need to find this. So then we have sine of 18 degrees. It's going to be dBdt over 275. So sine of 18. Yeah, that's the right answer. Okay, so this is equal to 84.9, basically 85 miles per hour. The question, the problem with this question is it doesn't tell you exactly what it's talking about. If I were in physics class, I would think that it gives us the horizontal speed, which is 275, but it's actually the angled up speed. I'm not going to worry about that type of problem. If I do give you that problem, I'm going to give you explicitly what's happening where. Like I'll draw a picture for you and give you the kind of the breakdown. So that's how you do it in green. If I wanted you to do it in red, I'd give you more information. But this is how it's done in green. It's way simpler than what it needs to be. I hope I'm not confusing you with that. I hope that answers your question. But that's the answer we're looking for. Limit as x approaches 0 of 3 times 1 minus cosine of x over x. Okay, this is a lot like one of the first ones we did. We can factor out that 3, so it's 3 times the limit as x approaches 0 of 1 minus cosine of x over x. That's one of our special limits. Okay, that's this middle one, and that's just equal to 0. So this is 3 times 0, which is just 0. Number 13 on chapter 1 test. Got it. Okay. 13 was hard. (13) says evaluate the limit as x approaches negative infinity of x plus square root of x squared plus 3. And I'm going to give you a hint and say that this is all over 1. And when we do that, that should give you a clue to rationalize. So we multiply by x minus rad x squared plus 3 over itself. That gives us x squared minus x squared plus 3 over x minus that stuff, which is equal to just negative 3 up top, and x minus rad x squared plus 3. And we're taking the limit as this approaches negative infinity. So once we get here, we can start to plug things in. Okay. Um, so if we, this top part, that's staying -3. So no matter what, that's -3. The bottom part, this is -infinity. We're plugging in a really big negative number. We're also plugging it in here. And when we plug in a negative really big number, squaring it, that becomes a really big positive number. Okay. This 3 right here doesn't matter in the long run because it's just a constant. What matters are these two things right here and right here. Okay. Because in terms of infinity, 3 means nothing. But what this is this is basically -infinity minus a square root of an x squared, which is a positive infinity. This negative distributes, so we have -infinity minus infinity, which is just equal to -infinity on the bottom. Okay, and then when we look at this entire fraction, we have -3 over a negative, so that gives us a positive. And as our denominator grows infinitely, the entire fraction goes to 0. So stop it. So this entire thing goes to 0. If it were a positive number, it would be a positive number, but it's going to be 0. That's a harder question. Let me find a different infinite question. We'll do something pretty easy. Can I do 10 on chapter 1 test? Yes. I'm going to do one more infinite question. For example, okay. For guys who went over asymptotes last year, this is really, really easy. But let's plug it in, right? So the limit as x approaches infinity of 4x squared over x to the fourth plus 3. When we're talking about infinity, again, constants don't really matter. We can kind of ignore this 3 and not have any problems. So really we're evaluating this thing. And what we need to look at is the degrees of both, because that tells us how fast the top and the bottom is growing. For on top, we're taking infinity and we're squaring it. On the bottom, we're taking infinity and also multiplying it by 4, I guess. We're taking the bottom and we're taking it to the power of 4. Okay? When we compare this thing and this thing, this is going to grow much, much faster when we go into infinity. It might be pretty close when we're anything from like 1 to 1,000, but as soon as we get to really, really, really big numbers, that denominator is going to grow a lot faster, which means our entire fraction is going to 0. $10 on chapter 1 test and then 18 and 19 on chapter 1 test? Yes. 10 on chapter 1. So I think the reason I put number 10 on there is because it was directly on the homework. But let's look at it. So limit as x approaches 0 of 1 minus e to the negative x over e to the x minus 1. This is a good question because it relies a lot on you being able to it requires a lot of knowledge from a lot of different places. Not a lot, just a couple. But it's asking you to understand powers, understand adding fractions, understand factoring things out. And when you do those things, it's actually not that hard. Okay, so this is really going to be the limit. I'm just going to keep rewriting it until it's really easy to deal with. So 1 minus e to the negative x is really 1 minus 1 over e to the x. Okay. This thing, we have a negative exponent, so it's dropping down to the denominator. So now we have this. Now we have to add these two fractions together. And if we do that, we got to get a common denominator, so this whole thing is going to be equal to the limit as x approaches infinity of e to the x over e to the x, right? That's the 1. That's this thing. Minus 1 over e to the x over e to the x minus 1. And then we actually have to do that subtraction. So this is the limit. This should be a 0. Didn't mean to do infinity. Of e to the x minus 1 in the numerator over e to the x in the numerator's denominator, numerator, over e to the x minus 1. Right, so this becomes this whole thing. Okay, now we have a fraction within a fraction. So this becomes e to the x minus 1 over, then we're just multiplying those two denominators together. So e to the x times e to the x minus 1. And now this becomes a lot easier. Okay, there's a common factor on top and bottom. So this whole thing is actually the limit as x approaches 0 of 1 divided by e to the x. Now we can plug in 0. Anything to the power of 0 is 1. So this whole thing is just equal to 1. So it's not bad once you actually simplify it. You just got to kind of finagle it first. Don't need 18 and 19. We can go over it once if we get a chance, but for now I'll skip over it. That was 10. We can do 11. 11's another one that looks really difficult, but it's not. This is the limit as x approaches 0 of cosine of x times tangent of x all over x. And again, you just got to use a little bit of prior knowledge. Tangent is sine over cosine. And I'll rewrite cosine as cosine over 1. Okay, so this numerator is this whole thing. And you should be able to see that cosine is a common factor on top and bottom. So this is actually the limit. This should be an x. This should be the limit as x approaches 0 of sine of x over 1 over x which is really just the limit as x approaches 0 of sine of x over x. This is a special limit. This thing is just equal to 1. Number 7 on the continuity quiz. Yeah, I need to find that real quick. Hold on. Okay, I'm gonna just scroll through because I don't know exactly which one you're talking about. It'd be after that, I know that. Koenig, if you could like take a picture of the problem and then email it to me and I'll do it. I don't know which one you're talking about. In the meantime, I'll do 18 and 19 on that chapter 1 test. I'll table that. So 18 says limit as x approaches infinity of 2x cubed minus 7x plus 1 over negative 3x to the fourth minus 100. Okay, again, really all we're doing is we're looking at the degree of the numerator and denominator and comparing them. The bottom's bigger, so it's going to grow faster. Okay, so you're going to get some big positive infinity up top, and you're going to get a negative 3 times a bigger infinity down bottom. So if you want to look at it like this, this isn't totally accurate. This kind of cancels 3 of those. So you get 1 over negative infinity, which is just going to go to 0. 19, limit as x approaches infinity of 14x to the fifth minus 8x cubed plus 4x minus 1 over negative 10x to the fifth plus 2x. Okay. When we're dealing with infinities, the only thing that matters are the bigger degrees, so we can get rid of all this other stuff. None of this matters. And really, we're looking at 14x to the fifth over negative 10x to the fifth. We can simplify that. These x to the fifths cancel, and you're just left with 14 over 10. So the whole thing is 7 over 5. Okay. That continuity quiz. Says let f be a function. Let f be the function. Defined by f of x is equal to 3x to the third plus 2x squared over x squared minus x. Which of the following statements is true? Okay. First state, well, let's just work this out. Okay. If we were taking the limit anywhere, the good thing to do would be to FOIL or to factor stuff out just to see what's happening with the entire thing. On top, you can factor out an x squared. And you're left with 3x plus 2. On the bottom, you can factor out an x, and you're left with x minus 1. Okay. We can factor out one of those with one of those. So we're left with x over x minus 1. Okay, so things we have. There's a hole at x equals 0, kind of. Yeah, so there's going to be a hole at x equals 0, but that's, yeah, it's, yeah, there's a hole at x equals 0. Okay. Because there's a hole at x equals 0 because we can factor out an x from the numerator and denominator. Okay. That's what... Yeah, that's what it means to have a hole in this case. Okay, you can factor out a numerator and denominator. So we can factor out an x and an x on the numerator and denominator. Therefore, there's a hole at x equals 0. Okay. There's also this vertical asymptote, this non-removable discontinuity, x minus 1 equals 0, so x equals 1. So there's a removable x equals 0. And an asymptote or non-removable at x equals 1. And that's because it's a vertical asymptote. Okay, so on just looking at your picture, the first option can't be true because there's not a vertical asymptote at x equals 0. At first glance, there is, but that can be factored out with an x on top. And because of that, that's no longer a vertical asymptote. It's a removable discontinuity. X equals 1 is still a vertical asymptote because you can't factor x minus 1 out from the top and the bottom. On 22 chapter 1 test, how do we figure out where an oscillation is and the difference between a jump oscillation? Jump and oscillation. Okay. An oscillation. Yes, and these two questions tie into one another. I'm going to answer Koenig's question first, just so we can stay on topic. They're similar, but they're not the same. So, types of discontinuities. A removable discontinuity is a hole. It's going to look like this. Okay, this happens when you get something that looks like this. Okay. The whole here would be when those common factors equal 0. And the reason it's a whole is because that point still exists in the function, but we can kind of factor it out and ignore it. But that point doesn't exist. Okay, because if this is our function, if this f of x is our function, that x plus 1 is still included in the numerator and denominator. But again, if we're graphing it, we can kind of ignore it. It just doesn't exist at that one single point. Okay, that's removable. A non-removable can happen in a lot of different ways. Okay. The most obvious one there's a lot of obvious ones. I'm not going to say the most obvious ones. So if we have a graph and we get a vertical asymptote, and let's say there's a horizontal asymptote for other reasons, our graph might look something like this. Okay, this vertical asymptote, that's non-removable. Okay, that's going to happen when you get something that looks like this, where you can't factor out that discontinuity. Okay, because we can't factor this thing out, when this thing equals 0, the graph just can't work. Okay, it's probably a bad example, but you get my point. That x equals those two, the graph and the thing I just wrote they don't match, but you get my point. When the denominator equals 0, you have vertical asymptotes unless you can factor it out, in which case it's a whole. Okay. Going on to other removable discontinuities, which gets to Smith's question. So this is a vertical asymptote. This is non-removable. Okay. Other types of discontinuities. If we have a graph that looks like this, okay, this is a discontinuity, right? If we were drawing this graph, we'd have to literally pick up our pen in order to draw that graph. That's a discontinuity. This, in this case, this is a jump discontinuity at x equals 2. This is non-removable. Basically, the way you can figure out the difference between a jump discontinuity and, a removable discontinuity and a non-removable discontinuity is if the limits on the left and the limits on the right are the same, right? So in this case, the limit on the left, let's say this is 3. right? That's the left-hand limit at x equals 2. On the right, this right-handed limit is equal to like -1. Okay, if those things don't match up, that's non-removable pretty much all the time. Okay, no matter what. Even in this case, it still works, right? The right-handed limit this case is positive infinity. The left-handed limit is negative infinity. And no matter what, if it goes to infinity, it's going to be a non-removable discontinuity. In this red case, though, the left-handed limit is still equal to the right-handed limit. The behavior on both sides are the same. Therefore, it's removable. We can kind of ignore it and still have the same type of graph. Can we put whole and asymptote instead of removable and non-removable? It depends on the question. If I just want you to classify non-removable and removable, I want you to actually use that language. If it's saying find asymptotes, I want you to use that language. In the context of calculus, it's normally going to be, well, it could be both. I don't see me putting that on the test, though. I think we're going to use removable and non-removable. Greetings from Argentina. Hello. I don't know who you are, but hello. How do you know if it is a horizontal asymptote? It is a horizontal asymptote if it's ever a rational function. Okay, so rational functions are always going to look something like some polynomial okay whatever. I don't know what that's going to look like, but it's going to be some polynomial over some polynomial, and there's most of the time there's going to be a horizontal asymptote. How do you know what type of horizontal it is? You need to compare the degree of the numerator and degree of denominator. And that's pretty much going to tell you what's happening. If the denominator is bigger, like it is in this case, this whole thing goes to the horizontal asymptote is 0. Okay. If the degree of the numerator is bigger, then there's probably a slant, in which case there's no horizontal asymptote, but the behavior is still unbounded. If the numerator and denominator degrees are equal, you're just taking the ratio of the leading coefficients. In other words, you're kind of canceling things out that don't matter. Will piecewise functions be on the test? There will probably be one. And I'll show you one. Just have to find it. Please hold. Okay, so one directly from the AP test says given f of x is equal to x cubed plus x minus 2 over x minus 1, for x not equal to 1. And some constant c for when x does equal 1. It's asking for what values of c, what value of c makes f of x continuous. And honestly, this isn't that big of a deal. In order for things to be continuous, you can't pick up your pen when you draw them. Okay? So it can look like a lot of things. But there has to be a point at every spot. So all you would do is you would take the thing that's not equal to 1 and set it equal to the other thing. But it has to be equal to the other thing when x is equal to 1. Whoops. So we'd plug 1 into x. We're going to run into a problem, though. So there's a little bit of work we got to do. Yeah, okay. How do I want to answer this? How do I want to explain it, rather? This looked harmless when I pulled it out. Of the book, don't. So it gives you options, and that'll help. So for what values of c is the graph of f continuous on the entire real number line? First one is -1. B is 0. C is 1. And D is 4. Okay. So we need to test that for C. And what we would do is we'd plug in 1. Basically, we just need we need the left-handed limit and the right-handed limit. So what we need to do is we need to find things on the left of 1. So we'd plug in something like 0.9. We evaluate it. Something to the right of 1. Evaluate that. That doesn't help me either. Why can't I answer this? Oh, the answer's 4. I know that. I'm just trying to figure out how to tell you how to answer it. graph it. That's easy. Yeah. You're just plugging in numbers really close to 1 from the left and the right. I think I just plugged that in wrong. Right? 1.1's cubed. Oh, I see. I just missed this -1. Yeah, so this is about 0.431, 4.31. And it's just going to be somewhere in the middle. I wouldn't, on a test where we have to cover a whole bunch of stuff, I wouldn't give that to you. What I would give you is something where the piecewise function is like 2 lines. I think the example I was doing with Davion today had something like, not that, that's an integral. Like ax plus 1 when x is equal to, or x is less than 3. And x squared plus 1 when x is greater than 3. Okay. In this case, we need to find what value of a makes this thing continuous. All right. And we would just set ax plus 1 equal to x squared plus 1 when x is equal to 3. So we would do 3a plus 1 is equal to 3 squared plus 1, and we'd solve for a. So 3a plus 1 is equal to 9 plus 1, so 3a plus 1 is equal to 10. So a is equal to 3. So if you have 3x plus 1 and you piecewise that with x squared plus 1, it's going to be continuous when we break it at x equals 3. Hello, Elijah. Nice to hear from you. Very carefully. That's how. There's some girthy problems. How many questions are we looking at on this final? I'll be honest. I'm gonna go and write it right after this. It's gonna be derivatives and limits, so it's probably gonna be a little bit longer than the last test, but covering limits. I'm also gonna have a graph, and I'm gonna ask you things about the graph, where it's continuous, where it's not continuous, what different points mean, and all that. All right. I'll leave this open for a couple minutes. If people have questions, I'll continue to answer them. But let's say at like 9:12, I'll call it then. Oh yeah, my bad. Oscillations. I never answered that. Oscillations. Oscillations are not like 1 over x. 1 over x has a non-removable discontinuity. That's because of an asymptote. An oscillation is going to look like the graph sine of 1 over x if you plug that into your calculator. Let's see if I can get a picture. Sine of 1 over x looks like this. All right. So an oscillation is just when something oscillates an infinite number of times in a really small space. So as this x approaches 0, this whole thing goes to infinity. And when you're going to infinity as you approach 0, basically it's just going up and down a whole bunch of times. In other words, if you're going around a circle, as you go toward the origin, you're spinning around the circle an infinite number of times. That's an oscillation. Okay? So there's oscillation, there's jump, and then there's unbounded behavior. Unbounded, that's like 1 over x. Okay, it's a bad graph, but that's 1 over x. That's unbounded behavior. And even if it's like this, if they're both going to infinity, that's technically still unbounded behavior, so it's the limit doesn't exist. This is an oscillation, and then there is a jump discontinuity, which just looks like this. Okay, that's a jump. Yes, your example for the limit is correct. If f of 2 is 1 and the limit as x approaches 2 is 4, that would be a jump. Well, not really. I can draw that without it. It's. I would consider that a removable. You're talking about. Come on. You're talking about something that looks like this. Okay, that is a removable discontinuity. For it to be a jump, the right-handed behavior is not equal to the left-handed behavior. So a jump would look like this. So a jump is in red, removable is still in blue. Cosine of 1 over x would still be an oscillation. And yes, I haven't written your entire test. I have a lot of it written, I just haven't totally completed it yet. Relax. Cosine of 1 over x is going to look a lot the same. Just looks more like a cosine instead of a sine. Like that. It's probably hard to see, but that's what it looks like. There you go. That's cosine of 1 over x. Yes, that's still an oscillation. Okay. I'll give it another couple minutes, and if no one asks any questions by like 9:17, I'm gonna call it. All right. So I'm gonna mute myself for a couple minutes, and then if no one asks anything, we'll be done. All right. Is the test basically one question from every unit? Uh, no, because that would just be 2 units. No, it's gonna be there's gonna be a couple derivative problems like that were on chapter 2 test. There's gonna be a couple just evaluate these limits, and there's gonna be probably 1 newtons, one related rates, um, and then a couple of questions about a couple of graphs. I think that's it. Don't hold me to that. I mean, there's going to be logarithmic differentiation. There's going to be implicit differentiation, but that's going to be under evaluate the derivative. Um, Newton's method, related rates, evaluate limits with special limits, and then questions about graphs. Yeah, that's all I have written. One over x is not an oscillation. 1/x is there's unbounded behavior. So again, 1/x is the rational function, and it's going to look like this thing in green. That is not an oscillation. Okay, it is not oscillating back and forth an infinite number of times. It's going off to infinity from the right and negative infinity to the left. It's not oscillating. An oscillation looks like this thing. Okay. As you go from the right, it's oscillating up and down an infinite number of times. As you move from the left, it's oscillating up and down an infinite number of times. It looks like there's a little small gap at 0, but that doesn't actually exist. That's just the graph. Okay, I'm going to call this. I'm going to shut it down. Again, this isn't meant to be all of your studying. This is just meant to guide some people and answer a couple of questions. Go over as many examples as you can. I'll be there before the final. Come in with questions, and then we'll get started once the bell rings. So I will see you guys tomorrow. Good luck. Get sleep. And yeah. All right.